Are we good? Hey, good evening, everyone. Hi, I'm Joe Arnold. I'm one of the founders of SwiftStack, and excited to be here tonight. And so I've been involved with OpenStack for like many years at this point, and I've always talked at the OpenStack Summit to talk about things inside of Swift. And this is the first time, though, that I'm talking about projects that have been coming around Swift. And I'm pretty excited about it. So let's get to it. There's a couple projects that are really enabling, or the goal here is to enable more broad use cases for Swift. And those are ProxyFS, and that's a open source file system. It integrates into OpenStack Swift. It provides one of the unique capabilities of providing object and file for the same data, and it happens to be written in Golang. It's Apache 2. And the other project is OneSpace. And this is a multi-cloud data management framework. And it integrates directly into Swift. And it's also separately deployable into the public cloud. So one of the philosophies that we've had as a company at SwiftStack is that anything that touches the data is open source. Okay? Anything that moves data is open source. And so for us, this is what we consider the modern Swift, well, stack, if you will. So obviously Swift, scale out object storage. The next one is called OneSpace. And what this does is it enables multi-cloud data management. So what we did was we just embarked on this project, and we contributed it back as open source, and it's Apache 2 licensed. And what it does is it manages a single namespace between two object API endpoints, so an S3 bucket and Swift buckets. And it can be used for things like data lifecycling, for data protection, data migration, things like that. And then there's ProxyFS, and that's the object storage system that we just talked about. And it provides object API support, so that's S3 and Swift, and it provides for file access with SMB and NFS for the same data. And what that means is that you don't necessarily need an extra file system gateway. That's going to be incorporated in part of ProxyFS. And then finally is Metasync, and that's something that we use to synchronize application metadata. So like think if it's videos, that would be camera type, things like that. If it's medical imaging, it would be patient information, things like that. And to sync that into a search index. So all these components, they all work together. And we're going to talk about the first three and how they work together to provide multi-cloud data management components. So what we've done over the past few years is we've focused, of course, on Swift as the core component for our product offering, and it's really served us really well. And what's interesting, though, is that we've been focusing on these really data-intensive workflows and work cases where there's this big data pool, and of course, Swift is a really good foundation for that. But when we started working with more and more customers, what we realized was that many of those workloads, they really needed file system API support. And it's like their applications should have been all along been using Object API, but there's just so much code out there. These applications are entrenched. I mean, even if they could change it, sometimes they can't. And rather than thinking about it from having separate systems, like the naive approach would be to have a gateway that comes along and provides that file access. But the other thing they wanted to do was be able to implement over a period of time object APIs on top of the system. So we thought that an integrated approach would work really well for us. And that's been helpful, and we'll talk through that. Just a note, I have a bunch of demos on our YouTube channel. You can go check those out. You can go to the website to take a look at the product and try it out. So it's self-service. OK, Swift object storage. So when we're going to do this multi-cloud stuff, we're building a file system. What do we need from Swift? Well, We need it to store data, right? It's a really reliable, it's scalable, has very high durability. The availability is just off the charts. The scaling, we're in these really large deployments, multi-region. You can distribute data across different data centers, fault tolerance, all this auditing. It's a really great and strong platform to build on top of. And the momentum behind the project, and this is, number of lines of code, maybe, okay, it's not the be-all, end-all metric, but I mean, I don't think many people realize that this upcoming release that's happening in June is the biggest release of Swift ever since the project was launched. And the momentum behind the project is incredibly strong. So this release, we fold in AWS S3 directly into the product. And even more impactful, what we've done is we've developed what we're calling container sharding or bucket sharding. And one of the attributes of people who've been building applications targeting AWS S3 is that you can have an unlimited amount of objects per bucket. And this matches the architectural parity so that Swift can also support unlimited number of objects per bucket. And we're really, really excited about this release that's coming up. And that brings us to OneSpace, which is multi-cloud data management. And so let's talk about what this is. When we started working on it, we were focused on, okay, well, what do people want to do? Why do they want to do multi-cloud data management? The first thing was doing data lifecycling. So that's connecting two object storage namespaces and lifecycling. Time is a good thing. Capacity is another way. To lifecycle data to that other storage location. Lifecycling it to yourself, whether that's to change the storage policy, or maybe you have two on-premises storage clusters and you want to lifecycle or you want to consolidate multiple clusters into one, or you want to lifecycle out to a public cloud and store the data there. And one of the things about OneSpace is that it connects those two namespaces, so when an API request is made, that the client doesn't need to change as the data is being lifecycled. The application can continue to run. You take that single namespace, and then you can start thinking about doing things like live migration. So how do you pull data from another source so to facilitate a live migration of an application? And at least with the customers that we've been working with, this is no easy feat. This is a big challenge because the data migrations take like weeks and months at a time, and you can't take a service outage. It's just impossible with these data sets. The network can't even support doing the data migration. So with this live migration functionality, what you do is you swap out the API endpoint behind the scenes of the client, and then you perform the migration, and that data can be migrated. The next thing is cloud bursting, so moving data out to the public cloud, or just providing access to the data in a public cloud so a computational workload can be bursted up. So we've been working with folks that have been doing bursting of workloads to the public cloud. And finally, data protection. Not everyone has multiple data centers, and so putting that data in a public cloud or another location, automatically doing some data protection, like preventing deletes from going across, enabling versioning, things like that, to provide some data protection. So here are the components of OneSpace, at least on the Swift side. So there's three components. One is middleware that runs in the Swift proxy, and it's the thing that creates the single namespace. And it will, when it asks for data, it will retrieve locally first before trying to retrieve from the remote location. Then there's two other components. One is attached to the container services, which does the life cycling and the mirroring. And that will operate on the data as it's coming in and make decisions about how to migrate the data or how to lifecycle the data. The third one can be deployed on any node in the cluster is the migration software. And what it does is it will pull the remote location to pull data in. So those are the three components. Then the second component here is there's a connector, something we call the Swift one-space connector, which is a container which can be deployed in the public cloud. And what it does is it mirrors the functionality on the on-premises SwiftStack cluster so you can get access to the on-premises data in the public cloud. And it also has the similar rules. When you go get data, it will retrieve locally, preferentially first, before going to the remote location. Any new data that's being written will be written into the public cloud, will be written into S3. So what that does is it allows you to have applications running in both locations. So you can have an application that's running on premises, you can have an application running in the public cloud, and they can both access that same set of data. And if you're in the room 2 sessions ago, there was a presentation from Cisco, for example, which was demonstrating an application bursting out to 2 different clouds between their on-premises environment and the public cloud. Well, what about the data that application is residing behind? That's what this is supposed to address. So you can take that application, especially in this world of bundling up applications via containers and bursting them out. You can also attach a one-space connector to get access to that same data pool. The other thing about integrating it directly into Swift is that it gives us the same attributes of Swift itself. We get the durability. We get the availability. It has the failover capability. So there's not just one process that's running to make sure that the data is being life-cycled. That work is being distributed across all of the container services and all of the nodes in the cluster that are doing those tasks. Just quickly, an example, like if anyone has had a kid and you've done genetic screening at a doctor's office, then you're more than likely have used council services. And they have genome sequencing. That data gets stored on premises, and then they lifecycle data up and out to the public cloud. They rerun and rebuild algorithms, but they need to run it across their whole data set. And what OneSpace does is it connects those namespaces together, so when they start doing analytics, whether that's in the public cloud or if they're writing so much of tools on premises, and then they can get access to the same data. All right, ProxyFS. This is the last session of the day. I assume everyone wants me to just jam through to get to this endpoint here. OK. ProxyFS, cloud file system. Talked about this, the Apache 2. There's an architecture reference at proxyfs.org. That's a little white paper, and the code's available at swiftstack.com/proxyfs. Likewise, OneSpace is available on github.com/swiftstack/OneSpace. So we started to build ProxyFS, and again, because we kept running into this, it's going to take 10 years to move our applications to cloud-native architectures. Yes, they're file. OK, great. But I can't go ask my development team to go re-architect every single application that is accessing the data via file system. Me, as an operator, I want to be able to provide storage as a service. I want object APIs. But I need something that can help facilitate this transition over a period of time. And so that was something that we really wanted to do, was make sure that we could facilitate that switch over a period of time. So this is what we ended up with. We ended up with a log-structured file system. When we went to go build this, it was important for it to not just be like a gateway. Gateways had 2 behaviors. On one hand, they would wrap the data up into a format so you could only access the data in and out through that file system gateway. Or they had the attribute of being file system-like, where they mapped a file directly into an object in the object storage system, but then they'd go, well, sorry, you can't rename a file. And even though when you try to sit down with people who are building these applications and you said, OK, you can do this, but you can't do X, Y, and Z file system operations, they had no idea if their application did that or not. So we had to accommodate the ability to make changes in the file system, be able to update data in the file system like a file system expects. So we had to make it a full POSIX file system. And the solution to that was to use take a log structured approach for storing data into the file system. And a log structured approach, what it does is any new data that comes in is a segment into the file system. It gets uniquely named and put in the backend object store. We present the file system via SMB, via a Samba VFS, and that's a C module that gets directly integrated into Samba. For NFS, there is a Ganesha VFS module, as well as, of course, you can locally mount a Fuse file system and then export that via NFSD. Then there's a module in the middleware, which provides for the S3 API and the Swift API. And then because we're doing a log-structured file system, that means snapshots are very easy, because we're continuously taking snapshots and checkpointing the state of the file system and storing that into the backend store. And for those who have been following Swift development very closely, that you would also notice, hey, don't you already have something like this for multi-part files? And of course, Swift and S3 both support multi-file uploads. And with Swift in particular with static large objects, which represents a manifest file with byte ranges, OK, really similar. But there's a little subtle difference with the log-structured file system approach. Instead of being like a table of contents, it's more like an index into the data. So it's a little bit different, but the concept isn't foreign inside of Swift. So what happens is segments come in, we update those segments with extents, and extents are just byte range references, and those are a big pile of B+ trees. And those B+ trees live in that file system, and they get serialized down and stored into these extents as new data is getting written in. And so when you go to modify a file, which in object you can't, right? You can't modify. There's no facility in an object API to say, hey, I don't like this part of this object. I can't update that. I want to go change that. You can't do that. You have to re-upload the entire file atomically. But with a file system, you must be able to do that. And so when a new segment comes in, we update that extent map and jam it into the file system. And then if there are any unused segment, garbage collection comes back around and sweeps that up and cleans that up. And so that's what gives us the ability to update files in the file system. And the same is true for the file system tree, right? So it too is part of that same file system. It's a pile of extents representing directories and the contents of those directories, the files, the metadata associated with them. And so that gives us an architecture that looks like this for ProxyFS. And starting with the further right, the Swift proxy side. So look what happens there. So you have an S3 client that comes in, and a request is made. Then there's middleware that will interpret the object API request and go, hey, ProxyFS, what log segments does this data map to? Then that middleware goes directly and fetches that data out of the object store and serves that back up to the client who's asking for it. And that's what gives it the ability to service those object API requests. It's not doing it through like a layer of file system. It's actually asking that there's a special API in ProxyFS to translate, hey, what does /user/cat.jpg translate into for log segments on the back end. So we can go fetch that data directly. And it's in every single proxy server in the stack. So that can scale out. And then look at the file serving and file access are different. So the ProxyFS VFS, written in C because it needs to be directly integrated into the Ganesha and the Samba layers, but it too is talking to the ProxyFS instance for metadata, and it too can talk directly to the backend object storage system. So that's the strategy of the architecture, is to build it in such a way that you can enable the scale out of these components, while still maintaining file system consistency by making sure file system metadata updates are all being funneled into something that can mediate that. Oh my gosh, this works great for streaming assets. So some of the early first use cases we've gotten has been a couple of surveillance and logistics companies that are, if you think about that space, they're doing new interesting things. They're wanting to build mobile applications and web applications. They're wanting to plug their data into things like data analytics, things like that. And so this gives them a path to do the modernization over a period of time. So it's been a good use case. OK, now putting all these things together. We got Swift, strong consistency, read your creates, which is super interesting because when data gets written into Swift, it doesn't just store it in some temporary location, then it goes off to replicate that out. No. When you write data into Swift, the client gets back a response. It's like, I got it. And it's been serialized down into the persistent storage in a durable way. Strong consistency, read your creates. If I have a new object that is uniquely named, that means nobody else could have used that name. And if I'm updating an object, and there's a situation where, say, a node goes down or a network connection gets severed, and if I have two writers that are writing the same data, they'll both work. And then when that network connection gets reestablished, what will happen is the system will automatically repair and have the newest write wins. So that's what we mean when we say eventually consistency rules. But if I'm writing new objects every single time into the system, like with ProxyFS and having a set of nuances that never ever repeat, then I'm guaranteed to have strong read-to-write consistency for new objects, which is a pretty cool property. It's an awesome building block for a log-structured file system. OK, then we have one space. And I'm creating a single object namespace between on-premises and public cloud or to another object storage. And I can do on-demand caching all day long. Remember, if I'm getting uniquely named log segments, I can just cache those all the time because they're guaranteed not to compete with each other. Or I can migrate them around. I can move the data around. So I can lifecycle data around. But anyway, so one space can give us the single namespace for those log segments. And then ProxyFS, which of course has the log structured file system, we can leverage the read your creates. All the persistence is in the object layer. So the file system is constantly checkpointing itself, creating snapshots, representing it. It has the module to integrate into that object API. Then ProxyFS can become extremely portable to wherever it can get access to the underlying data. So kind of combining these together, we can bring and overlay ProxyFS on top of Swift. We can overlay it on top of one space, and then we can share that single namespace for all the log segments and all the checkpointing information. And we can have the ProxyFS deployed on premises with the Swift cluster, and we can also have deployed on top of a container on top of one space and have the persistence be something like AWS S3. And so in order to do this, what we've done is we mount from snapshots, and we'll do periodic fast forwarding and merge. So it's not about having a consistent file system view between some on-premises location and in a remote location, and passing global write locks and ensuring that the consistency. That's just almost impossible to do for the workflows that at least this is intended to take on. It's not about trying to distribute a database or a CAD file or anything like that. It's about these data streams, big data footprints, where you're wanting to do data processing and data access in the two separate locations. So it's minutes consistency between seeing data show up in the other location, not trying to be an instantaneous view of the same file system. So one space then shares that local cache of the log segments and does opportunistic caching of the log segments or purging to reclaim space. And then this is a picture that we draw for the folks that we've been working with. So mount from a read-only snapshot into the public cloud, burst up the workload, and then move the application so they can see the data. And if you want to read-write, do so with an overlay strategy and overlay a read-write and a write file system and merge down. Merge down so that then you do conflict resolution at the merge time and synchronize those two namespaces together. One space syncs the log segments. So if if the file system asks for a log segment and it's not there, it will bring it across and it will cache it. And that enables that application portability, so you can have the file system access for that set of data in the public cloud. So that's the strategy. We really design these things so they can all work together. They plug into each other. Takes advantages of the scale of Swift, and it plugs into that environment. ProxyFS has been really designed for these workloads where you need to make this transition between object and file, and yet those applications don't support objects, so you want to be able to support that natively with the file system. This is the last session between now and drinks for everyone, and if anyone has questions, I will be happy to stick around to answer any questions folks may have. So thanks. Oh yeah, go ahead.
Sure, don't kill me, please. So do you have any kind of mapping of permissions between different domains, like file protocols, object protocols?
Yeah, that's an awesome question. So the strategy is to make them independent. They are so different. Like, I mean, there's enough differences between SMB and NFS on the permission side, which is we recommend with our commercial product, we don't deploy SMB and NFS simultaneously. You can all go configure it and do that if you want to, but there's enough on the permission side to make that complex. What we've done is we've mapped those independently. So that could be, in our commercial offering, we have an Active Directory or an LDAP mapping that could be configured for SMB. And then separately, you can configure Active Directory and AD on the object side. And those are configured independently of each other. That was our strategy. It's a good question, yeah.
Quick question. On ProxyFS, do you run into any equivalent of inode limitation issues for file count, directory counts, or is there any kind of scale recommendation? Yeah,
that's a good question. So the real thing to worry about would be on the nuance and extent mapping namespace, and I can't remember if it's SMB or NFS has different size limitations of them, and based on the frequency and how much data gets checked in and the use cases, we finally calculated out to be some hundreds of millions of years that we would not run out of space on the inode namespace.
Okay.
So no.
It scales? Okay.
Yeah. But there was a big internal debate on whether we could have eaten into that namespace to do snapshottings or not. So it's a good question. Yeah.
So with the log segment objects, I like what they bring to the table, but I'm thinking about from the Swift side. So if I have an application that speaks Swift API today, and sometimes in the application, say Hadoop or Spark, it wants to rename an object, which is a server-side copy. Am I able to take advantage from the Swift side of the same advantages of, say, appending to an object, changing a little bit in the middle, or renaming it through the Swift API today?
So we did implement a new API on the Swift side, which is called coalesce. And we did that to support large objects because if you wrote a manifest file, Swift clients might not appreciate seeing just a manifest file. So we wrote this utility called coalesce that merges a set of files together. So yeah, you could actually, using the Swift API, again, on proxyfs.org, you'll see a list of the APIs that we provided. And I believe we could use coalesce to do exactly what you're saying, which is to say, take these objects and coalesce them into this new object. And I think it would do what you want it to do, but I'd have to double check that.
Great, thanks.
Mm-hmm.
Hi, with the ProxyFS VFS to NFS Ganesha, for example, I guess would the intention to be sort of to run one of those per tenant, sort of a la Manila, or?
It's a good question. We haven't explored Manila integration yet, although we're extremely
Well, I
open
didn't
to
say
that.
it had to work with Manila. It's sort of the idea of here's your big pool of data out here, and how do you make it look like POSIX to all of a user's VMs in their tenant?
So it's a network file system, right? So you just export that file system, and clients via network file system protocols would mount that that volume. Yeah.
Any limits to the number of instances of that you can run in terms of scaling out?
I mean, we've made recommendations right now
storage.
with the customers that are using it to be in the hundreds of simultaneous connections that we've recommended, but that's just because of that. We wanted to scope out what we test.
Right.
But yeah, the idea between separating out the file serving from the file system is that we could scale out those things independently, and we can do things like failover on the file system node. So there's another feature of the file system node, the thing that's keeping track of all the inodes, is as it's checkpointing data back into Swift, those checkpoints, it's also simultaneously on the local node writing a replay log of itself. And that if you are clever, you can stream that out to other nodes to give high availability to the file serving node, and then the file access node, and then the file serving node can be clustered separately.
So there's maybe a bit more complexity to it than I was thinking, but it sounds like it's doable.
Yes.
All right.
Hi. As a file system, how the access management is controlled or handled? What users have access?
Yeah, with NFS, it's network-based permissions, and then with SMB, there's Active Directory integration.
Okay.
Or you can just define users that exist locally on the nodes and control access that way with a username password for SMB.
So NFS, if the user permissions are set there in NFS using NFS command, and they get replicated on Swift.
So then you're going to have to map. Well, if it's an NFS and you're mapping it to other Unix systems, then you're going to have to make sure that those users are properly managed across all the systems that are mounting it, right? And I don't believe we expose root squashing. I think that can be exposed in the configuration. Yeah.
Hello. I'm sorry, I'm extending. Or
bring it on. That's great.
Definitely, it's very, very highly awaited for feature. I have a question actually on the benchmarking. I mean, do you have any data that you shared on the website about that? I mean, especially, I mean, we're trying to compare it to other solutions, so we're trying to see kind of how viable it is.
Yeah, what we're doing, our strategy has been to focus on specific use cases with the partners that we've been working with. And I pulled up the video surveillance example, and like we're being deployed in this logistics company right now, and we can handle twice as many video streams as one of their current solutions can, and doing really, really well on maximizing the network bandwidth on those nodes. So yeah, I mean, we're doing pretty well from a throughput point of view for the use cases that we're targeting.
Nice, thank you.
Hey, so we at eBay use SwiftStack. Works pretty great, and we recently used OneSpace for our cluster migration. Thanks for your support. It works awesome. Thank you for that. Just that I don't have any question. Shameless plug, on Wednesday, 5:30 p.m., we have a session on running Swift at scale and what challenges we ran into at eBay. And please do attend. I'm sure folks would be interested to know. Thank you.
Yeah, thanks for that. Here, some other talk. Yeah, some other talks. We have we have the eBay talk that's coming up on your Wednesday at 5:30, right? And then we have John Dickinson, the Swift PTL. He's doing it on Thursday in midday for a project update, and then we have NTT doing a talk on Thursday at 4:40 on machine learning. So there's some cool talks that are coming up with Swift. So.
Yes, one more question regarding scalability. How do you handle deep directory structures, which are something that is natural and handled by inodes in a POSIX file system, while in an S3 or Swift object store, this is something that naturally doesn't exist?
Yeah, good question. So you do have this natural limitation of how long a URL can be for an object, right? And there's, I'm trying to remember the exact length that URL can be, but it's some 1,000? I think it's like 1024. 1024.
We work with people. We often find that the file system's a limiter because both in Windows and in Mac, you have a limit of 260 characters, and that's your path plus the actual file name. And in Swift API, you're talking 1024. So we actually have most of the time the opposite problem. You know, Swift can handle far more than the file system.
Yeah, so Doug, just for the people online, Doug was saying people see more of the limit on the file system side in terms of how deep that structure can be versus what you see on the file system side. And it's really not deep files, it's deep directories. It's more about the quantity of files in a single directory that's a challenge. And so we do use a B+ tree, and that helps out because it can be a shallow data structure to help support that.
My question was more about, not about path length, which is, as you say, deeper in an object file system than in a POSIX file system. What I was referring to is efficient handling of directories that have thousands of entries.
Yeah, so that's a really great question. That's right. That's right.
Object file systems to list a directory that has, let's say, millions of subdirectories and.
So that's actually So the question was how do you do the listing of something that has very, very, very deep directories? And if you're talking about doing like a pwalk, for example, on like a whole file system, and especially as file systems start becoming extremely large. Like right now, we're working with a file system that has, how many files does it have? It has like hundreds and hundreds of thousands of files in it, right? And the trick is you have to page in and page out what's in the file system, and be able to, so that B+ tree, that data structure, as it's loading data up, it will flush out old stuff out to disk. So it will page out and it will page in data as it needs to. And then it's about the limitations on what type of storage you're storing the file system checkpoint data onto. That can be a separate storage policy inside of Swift. How fast can you retrieve that data to load it up into RAM? How fast can you process that and read through that B+ tree? So it does do paging, and it pages out. So, all right, thanks everyone. Thanks for your time and sticking around late for this.